Rob,
Oh, hey. Yes. Question?
Yeah, in the previous slides about the collective MPIO, I don't see how many aggregators you used in all the slides. Like, could you tell me how many did you use and how to set those aggregators? Should I use the MPIO command, Romeo IO commands to get the aggregators? And could you tell me more about it?
Sure. When I ran this benchmark, I didn't do a whole lot of tuning on the aggregators. The Cray MPIO library has makes some guesses. I think it's it guesses at a few processes per node. In this case, I think it's 16 processes per node. And so what I need to say is there are definitely tuning parameters on how you can pick the aggregators, how many aggregators should be used. I was not able to get a dramatic difference in performance when I used some of the newer optimizations that were supposed to help, but I'm looking forward to exploring that a little bit more and seeing what I did wrong there. Maybe there's something else going on. There are some. So to the first order, if you just run this code on Polaris, you'll get pretty good. You get a pretty good number of aggregators. You can experiment with how many aggregators per node you might want, and that's probably a useful optimization, or sorry, useful experiment. But the default parameters here seem to be not too bad. So we can look at, I don't know if I should dare flip over to a terminal and show you the output. I won't do that right now. I won't do a live experiment of that. Inside the GitHub repository, I have the output files for each IOR run. And I asked IOR to tell me the hints, the MPIO hints that were set for this file when we so there were the hints that I requested and the hints that that the library provided by default. And you can ask the library, give me all the hints that you set, and it'll tell me something about things. And so it'll tell you how many aggregators were used. The hint is called CB nodes, CB_ nodes. And we can look at that a little more closely and see how many the library guessed was the right number to use, and versus how many we should have used. We can experiment with that. So okay, the short answer to your question, that was a lot of words. The short answer was for these experiments I just used the default settings, and I do have some experiments where I experimented with different values and didn't see too much change in the results.
Okay, so I was hoping to see if Darshan can show us beautiful ways of how just the aggregators are finally writing down to the file system, or is there a way to visualize the aggregators used to write the final writes in Darshan?
I'm thinking about different approaches on that. If you wanted to know which processes were involved, you'd probably have to ask. Oh, yeah, sorry, right. We go back here to that information is somewhere in the file because we can go back to our heat maps. I'm going way back here. And if we go back to the Darshan heat map, it will demonstrate that in this case, out of the 252 processes that were writing to the file, some small number were picked as aggregators. In this case, it looks like it was 4 of the processes were picked as aggregators. Maybe that's 8 processes were picked as aggregators. So how would you so an answer to that is if I would say that if the existing Darshan statistics are not quite answering the questions you have, we're always looking for ways of modifying the data collected and data reported so that it does answer the questions that people have. I think we can get the information with extra detailed logging right now. It may be that it needs to have a little more let me.
So this is great.
Go ahead.
So this is another way to get my answer, right? So this clearly shows 4 or maybe 2 for each black line on the right plot is the number of aggregators. So yeah, so this answers the question. So this gives the number of ranks which are used as aggregators, maybe not specifically on rank 197 or number, but it shows who did the final write. So this helps. Thanks.
Okay, great. So to wrap up MPIO, there are a couple of library implementations out there. The Romeo version that we work on at Argonne is the basis of a lot of vendor MPIs. So Cray has taken, sorry, HPE Cray has taken MPitch and made a few modifications to the MPIO library, especially with respect to luster tuning and performance and luster parameters for adjusting things. This discussion of the two-phase algorithms and who should do what, there is a parameter called the lock ahead mode, and there's a hint you can set to request a different locking mode, and then once you set that mode, you can ask for a multiplier. You may find for certain workloads having even more aggregators involved is better than the default number. Again, for these workloads, I was hoping to show some data that showed how important those parameters were, but they all ended up being the same result. So I got to figure out more about what's going on there. So the other main MPIO implementation is from the OpenMPI folks. OpenMPI has an OMPI-IO, which I would say that its big differentiating feature is that it's a little more tightly integrated into the MPI implementation. And so things like non-blocking operations are more integrated into the progress engine. And that's a bit of a nitty-gritty detail, but what it results is that for some cases, they're able to make a little more background progress. And the challenge is, as they adapt to different file systems, the file system specific optimizations are pretty good in Romeo. So sometimes they'll fall back to the Romeo implementation if they don't have anything particularly clever, more clever than what Romeo is already offering. So it's another option out there. I believe you can try it out on the Spectrum MPI based MPIs, like on Oak Ridge's Summit and Machine, but you'll see a lot of Romeo based implementations in some form of these different processes. And I've got a small blog where every so often I'll write about some new feature out there over on the cells webpage. But the important part about Romeo is that there's this modular file system feature where as new file systems show up, we can produce a new driver for Romeo that encapsulates all that file system specific information and makes it isolates that information from the users. They don't have to worry about whether they're writing to Luster or GPFS. At some point, they can get pretty good performance out of the box no matter which file system they're working on, as long as we've done our job and tuned it appropriately at that driver, which is always a kind of every machine's a new adventure there. In fact, after this talk, I'm going to talk to another storage developer about what it takes to get another driver into Romeo, and we'll have a little conversation about what Romeo expects and what the library can provide, and what we might be able to do there. All right. Any other questions about MPIO or two-phase collective buffering or data sieving or Darshan logs of those features? Great. Sorry, my phone keeps ringing. I'm not sure why. So let's talk about another turn of the crank to make it easier for applications to use these libraries. Make sure I'm on time here. Great. I'm doing fantastic. As we talked at the very beginning, applications don't think about bytes on disks. They're typically thinking about some kind of scientific data structure. And when they write that data, it would be great to use that data somewhere else. So the notion of a portable self-describing file format means that the file contains not just the information that the user wanted, but has a little bit of extra metadata describing how that data was created, the layout of the data, the architecture of the data, and the structure of that data, most importantly. And so I, knowing nothing about how an HDF5 or a Parallel-NetCDF file was created, can look at it with tools or applications or code and see, oh, okay, this contains 6 variables. They're 5-dimensional variables. They have floating point data in here, whatever the answer might be. And that self-describing nature ends up being a pretty big selling point when you want to deal with data management of these data sets, and not just for your own simulation codes, but other people using that data for analysis or AI training or whatever's happening. And having this structure, this self-describing structure, goes a long way. And in this case, we're going to talk about high-level libraries that are based on MPI-IO. Again, you can imagine domains where MPI and MPI-IO are not the right fit for their application. We don't see too many of those kind of domains yet, but as they get developed, I'll be happy to expand these kind of talks to cover those. I'm going to start off with a fairly simple interface called Parallel-NetCDF. It's one of the older self-describing file formats. When we started this project, there was only a serial NetCDF from the Unidata folks, and it was very widely used in climate and weather codes. But there was no way to write it in parallel. Instead, if you used it in a parallel code, you would send all the data to rank 0, who would then write it out. And you can imagine that's an obvious bottleneck. So it blows up memory on rank 0. It just makes things very slow. So the Parallel-NetCDF interface maintains the NetCDF data file format, but has a different API that's more natural for parallel programming. It's built on top of MPI-IO. It exposes collectives and communicators in a way that seems to work out pretty well for those climate codes. Now, there are some limitations in how you can use this file format and API, but we've seen it to be pretty effective for certain classes of climate codes. The NetCDF model, all these libraries have the same sort of notion. Over here on the left is a sort of the way that the application would think about the data. Maybe a chunk of atmosphere. It has 3 dimensions. It has a region in the atmosphere. Or maybe a patch of the ground. You want to check the surface temperature, surface pressure. And that is how the code thinks about it. Now, inside NetCDF, there is a header which describes the data type of the data, some annotations on the data, and in a very low level detail, the starting offset of that variable. Where in the file can you find this variable? And after the header, then comes all the data for one variable, and then all the data for a second variable. And again, that detail is hidden from the user. The user just thinks about arrays. There is a record variable feature in NetCDF and in Parallel-NetCDF, and this was one of those areas of the code that kind of tripped us up a little bit. In a record variable, so as I said, the data is stored in NetCDF as multidimensional arrays of typed data. But if you had something like a sensor out in the plains measuring wind speed at every minute, that variable will grow over time. And so they have record variables. And so these record variables might have a fixed dimension, the latitude and longitude of the sensor. But then the unlimited dimension, the record variable part, would be the time. And if there's only one of these record variables in the file, that's not such a big deal. But if there are multiple record variables, then the data is interleaved like a deck of cards, and that can be that can generate a non-contiguous access that, as we saw from our MPIO example, could result in pretty poor performance if you're not careful. So this is a tuning and an IO performance talk, but for Parallel-NetCDF, the tuning parameters are fairly limited. Using Parallel-NetCDF is almost enough in itself because it passes directly through down to the MPIO calls. There's a very thin layer in Parallel-NetCDF. So all that work happens underneath Parallel-NetCDF. The Parallel-NetCDF API choices that you use end up mattering a little bit more than which tuning parameters you're using. And of course, as I mentioned, the record variables complicate things, but I think we've got some ways of managing that through very careful tuning of the different optimizations. So MPIO is the foundation upon which Parallel-NetCDF rests. And so to tune Parallel-NetCDF, you just create an info object like you would in MPIO. And then you can say things like the striping factor you want for this file, or you can turn off optimizations like data sieving. And then you pass this info object into the CMPI create call. And that will collectively create the file, and you'll get an identifier back. And you've done that with all these MPI. And for the most part, users don't set these info objects. For the most part, things do okay. It's only when they come to us and say, hey, I've got a problem with X or Y, we look at the Darshan logs and say, okay, well, why don't we adjust this internal parameter a little bit for your case and see if we can get some better performance out of here. For the most part, and I think the Darshan logs bear this out, Parallel-NetCDF users hardly ever set tuning parameters. Now, there are some, and again, there's some, in this example, we used MPIO tuning parameters. There are a couple things you can do to carefully control the layout of the variables in the file. There's some extra padding you can insert to things. If you want to make sure all the data structures are aligned to a certain megabyte boundary, for example, you can trade up some space. You can trade off some space in the Parallel-NetCDF file for those for that alignment feature. We also use these info objects to help direct some experimental features. So, for example, Awaking's got some students working on burst buffering or logging of data, and those tuning parameters can help experiment with that while the researchers nail down those features before they're rolled into the real final library. So I want to just reiterate the difference, the programming model that happens between Parallel-NetCDF and the MPIO library underneath it. We don't talk about creating subarrays with MPI data types. We don't talk about MPI file write all. Instead, we talk about array information. In this case, a 1024 by 1024 array. Maybe it's a floating point number or something like that. And that description of at the array level, sort of at the Parallel-NetCDF level, is done in terms of the start of an array and a count in an array. I guess you probably had a little figure here, but in this case, it would be a simple 1D array. You might start at 0 and you might count in 4 in one dimension. So 1, 2, 3, 4. Write those 4 blocks out. But down under at the MPIO layer, that looks like starting at offset 2035, write the next 16 bytes out, and there's less contextual information there, which is fine. The application has described its I/O in a way that's natural to the application. The MPIO layer gets bytes and offsets, and that's the way things work in the software stack. There's a fun optimization that Parallel-NetCDF lets us do, though, called a write combining or operation combining optimization. It doesn't have to be for writes, so that's a mistake. It can be for writes or reads, where you, instead of using the collective calls, you use the non-blocking calls. And in Parallel-NetCDF, the non-blocking calls have an I in the name. So NCMPI, I put Vera says, schedule the write for this purple variable. Then you have another request, schedule the write for the orange variable. And then in the green here, then you do a collective wait and you write the data out. So here's a little toy program where you write out some variables to the data set. And if you do that one variable at a time, you get a lot of collective writes. But if you only wait to the last moment, then it's all done in a single operation, or maybe it's done in a few operations because there's one MPIO call per variable, and there's some variables here. So it all boils down to one right here. So again, over in our GitHub page, you can try out the toy example here. If you want to play around with these different interfaces. So I thought that might be. I was trying to mimic what happens with a code that does a little bit of computation between each IO phase. So in this case, there's some variables. You write out 5 variables to the file. You do a little bit of work between each variable, and then you do a collective call. Now you can see here, I try to perturb that sleep a little bit. I wanted to see what would happen if you had laggard processes enter the collective. Over in the non-blocking case, it's very similar. We have the 5 variables. They're possibly delaying a little bit between each time they issue a write operation. But when it's an I put here, a non-blocking write, we don't have to wait for all the processes to enter. We can continue on to the next round. Now there's some memory reuse, some buffer rules here. You don't want to touch this. You don't want to modify this buffer until the write completes in the NCMPI wait all call. But that's not so different from MPI non-blocking semantics either. Okay, so in this case, we're going to wait for however many variables we have, and we'll get back some status objects, and then we can talk about what happened using Darshan to see how it looks. So in this case, I would draw a couple attentions here. I don't know what's going on with this big orange patch here. So for 10 seconds, something at the MPIO layer happened, and that seems like maybe there's a bug in the Darshan report here. I don't know of anything that would happen for 10 seconds in the MPI library. So I might do some investigating there about what's going on. So I've got, so there's not only are these heat maps full of information, but I've got 4 of them here. The left column is what the MPIO layer sees, and the right column is what the POSIX layer sees. So you can look, if you look left to right, you see what transformations are happening from the MPIO layer to the POSIX layer. Going top down, the top row is the one at a time case. So we issue 4 of these NCMPI write calls. And those turn into a subset of processes writing out data to the data set. Now, I was doing the write of a column of a 2D array. So this is a non-contiguous pattern. And the chance here for the MPIO library to transform that request pattern into something that's a little more friendly to the file system. And here we have those histograms again, showing that some processes are aggregators that are doing lots of I/O, and some processes are not doing any I/O. And over in the blocking case, there's these phases. You can clearly see 1, 2, 3, 4, 5 of those variable writes. If we defer all that right to the end, then it's just one round of I/O. A little bit of a spike here. Probably two collective phase, probably 2 rounds of 2-phase I/O. But there was this. All the variables collapsed into one round of collective writing. What I was hoping to see was a little more delay as the work happened in these cases. That the non-blocking case would be more efficient and let the work happen without the I/O getting in the way. But I don't know, maybe I needed more time between iterations, or there's something going on that I didn't quite understand. Still, I think seeing the reduction in iterations is still pretty clear. And if that's a programming model that fits your needs, then it's another chance to get a boost in performance. Yeah. So I went through Parallel-NetCDF pretty fast. If anybody's using Parallel-NetCDF, I can talk more about it. It's not, like I say, it has a lot of use in the climate community, but it's not used outside of climate too much. Instead, I'll talk about the HDF5 library, which is used in a few more domains and has some different design trade-offs. But I'm happy to talk about Parallel-NetCDF a little bit if anybody has questions. All right. Let me head on to HDF5. So in a lot of ways, HDF5 looks a lot like Parallel-NetCDF. They're multidimensional. It's a data set library where you write multidimensional arrays of type data. The differences are that HDF5 has a little bit more sophisticated way of describing non-contiguous I/O using its hyperslabs. We won't talk too much about those. We'll touch on them a little bit. And it has a little more flexible way of doing the I/O in the background. The way it's storing the I/O. There's optional compression of data. There's optional filtering of the data. Some of that doesn't play well with parallel I/O too much, but it's a feature of the library that we can work with. And the H in HDF5 refers to the hierarchical nature. I got to figure on the next slide. We'll talk about that. And the variables aren't quite as restrictive as they are in the Parallel-NetCDF case. You can resize variables and grow them over time. That flexibility comes at a cost. The file format is a little more complicated, but it seems like that's a reasonable trade-off for a lot of applications. So again, the H is hierarchical. So you think about your file system on a Linux system. You have a root file system and a root directory and home directories, and then your own stuff in there. Well, in a similar fashion, you can represent the file system inside the data set, where you have a parent group that contains maybe some visualization data or maybe some output of a simulation, and each of those components is organized based on these groups. In the NETCDF case, you can kind of get this with conventions. You might say everything's got a dot in it if it's going to be a hierarchy, but that's made explicit in HDF5. HDF5 was originally a serial library that they added parallel features to, and you can sort of see that bolted on nature through the use of property lists. When we tune for parallel HDF5, this slide and the next slide are almost the only thing that needs to happen. We have to make sure that we use these property lists to request MPI IO. So there's a file access property list that we set up, and then we tell it, hey, we'll pass these communicators and these info objects into there when we create the file. And then when we do the IO, we're creating what's called a data set transfer property list. And so we can turn on MPI IO collectives. We have to opt into those collectives because, as we mentioned before, collectives require all processes to participate. And so if you have a code that is irregular in workload or in times, maybe collective IO isn't the right choice. But if it is, you can get some pretty good performance gains by turning on collective IO. And so again, call out to our GitHub page where we've got a small HDF5 example, and then we've got some Darshan heat maps talking about what the differences are between independent and collective IO. So again, left to right, you should be familiar with this now. You can observe what, if any, transformations happen at the MPI IO layer. The top is what happens in the independent case. Not much. With independent IO, there's not a lot of opportunities to change the IO around or do any sort of optimizations here. And so we're not able to there's really not much we can do here. And so you see these variables, we have writing happening in the first part and reading happening in the second part, but you really can't change anything. And so all these operations for every process turn into an IO, turn into an MPIO operation, which in turn turns into a POSIX operation. And you're not going to see great performance with this uncoordinated access to the file system. But if we do a couple of things, we could turn on, we turn on the collective IO like with this property list. And now all of a sudden, these MPIO requests boil down to a small number of POSIX requests. We see two-phase collective buffering happening here. We see transformations happening so that everything's nice and compact, not compact, but compact in time. Everything's right. I should point out that the runtime here went from 400 seconds in the POSIX case down to 32 seconds in the collective case. So, factor of 10 faster. That's great. And there's a lot of times when I will come talk to an HDF5 using application and figuring out how to get collective IO turned on is the one magic trick that makes things work well for HDF5. They're going even further with collective metadata optimizations. The metadata operations of metadata in HDF5. Sorry, in a file system, we have metadata like the name of the file, who owns the file, the date stamped on the file. In HDF5, the metadata is things like, where is this block of data located? There's some data structures that keep track of things, some indexes that record what's written into the file where. And if we use collective metadata, and we're careful with the routines we call, we can really reduce the number of those small metadata updates that happen both in the reading and the writing case. One process interrogates the file, figures out where all the blocks of data are, and then tells the other processes with the broadcast to say what the data is. Similarly, with a read, one process reads the index, tells all the other processes involved how that data is laid out. So I didn't get a chance to test out the asynchronous HDF5 features. I think that's fairly new. HDF5 1.14 was released back in November, of last year. I think was maybe earlier this year. So I would like to try that out and see if there really is as much background IO happening as was advertised when this feature was announced as in development. And then there's also the multi-data set IO, which looks a lot like Parallel-NetCDF's operation combining optimization, where you would set up a bunch of different operations and then decouple the execution of the operations from the description of those operations. So you post 10 data set writes and then wait for completion and then see what happens there. I think those two features if the application is suited for those optimizations, might be pretty good for seeing performance gains. So there are a lot of high-level libraries. Some of them are, talk about Parallel-NetCDF and HDF5. A lot of them are built on HDF5. My favorite example is H5Part, which takes the 300 routines of the HDF5 API and distills them down to the 7 that you need to do particle accelerator codes. Open a file, describe these particles, and then either read them or write them, and then close the file. And that's a perfectly valid approach to these high-level libraries. If it's too complicated, add another simplifying library to provide what the users need and no more. Now, this list is missing a machine learning library. I would love to see a machine learning AI framework of IO and the equivalent of MPI, right? Almost everything running on these machines using MPI. So MPI IO and libraries using MPI IO can help many codes in a way that's portable to all these codes. In the machine learning world, things are still a little bit dynamic. There's not really one middleware layer here yet. So I hope over time, and not too much time, we can find something like that.
Rob, there is this library called DLIO. Have you heard about it?
Have I? have I got a slide for you? Just wait 2 more slides and we'll talk a little bit about DLIO. Yeah. Yeah, that's exciting. I had a lot of fun playing around with that. So, spoiler alert. Yeah, I'm going to talk about machine learning workloads and how DLIO is a helpful tool in that in the next section. Yeah. All right. Well, let's go in.